Okay, so today is a very exciting lecture. We're basically going to take everything that we learned from Bitcoin, all the distributed networks and the cool technologies, and we're going to take the next step and apply it to like the world. We're going to talk about decentralizing the future and Ethereum and smart contracts, and then Aparna is going to go into like a bunch of examples of when we want to do decentralized apps and smart contracts, and kind of make you kind of like a consultant in the blockchain space. You can make informed decisions about when to use a blockchain and when not to. If you're just coming in, like, don't do the quiz yet. Just do it at the end of the lecture. It might actually help you to do that. And just, we're starting the lecture now. Okay, so I'm going to start with smart contracts. But first, we got a lot of feedback saying like, oh, we want to make the lectures more interactive. So I want to pose a question to you guys if you're up to answering. What makes Bitcoin so special? Like, what is the really like underlying technology that we are so excited about and we spend so much money and so much time talking about? Does anyone have any answers that they'd like to share? Blockchain, yeah. Anything else? Okay, chill. We got one answer. So my answer to this question is the idea of a distributed network. If you were totally lost in the last 4 weeks, or I don't know, you're just finding this lecture online or something, and you have no context, what I want you guys to remember is this idea of distributed networks. And this is composed of 3 like magical parts that make this formula. The first is cryptographic identities, right? Public and private key cryptography that allow you to reveal absolutely no information about yourself, but still be able to consistently authenticate transactions, prove ownership of some digital asset, and attribute accountability or blame to somebody for their past actions, even though you don't know who they are, even though the system is like anonymous or pseudonymous. And the second portion is this innovation that Bitcoin introduced, which is a consensus protocol. Even though we don't know the other people on the network, and there can be people with multiple nodes or more power in the regular world, we can make a democratic decision using some kind of consensus protocol, such as proof of work or proof of stake, or other alternative consensus protocols. And the third is the blockchain, like you said. This lets us have an immutable source of truth. It's a ledger that we can add to, but not edit afterward. And this is really, really valuable as a data structure when we're talking about keeping things secure and distributed. And so there's a lot of benefits when we have a distributed network. If you remember this buzzword slide that Nadir put up on the first lecture, we get trustlessness, right? I don't need to know who you are and you don't need to know who I am, but we can come to an agreement and everyone in the network can come to an agreement and trust that because of this consensus protocol, this decision that we made is in the best interest of all of us. We also have an awesome immutable ledger of truth. This is usually how I like to frame blockchains for other people to understand that once we make a decision, it can't be unmade. Once something happens, we can't go back and change it. There's no central point of failure or way for one person to take control of the network because of all these great technologies. And this is really exciting, right? So a lot of people said, like, why don't we put everything on a blockchain? Like, why don't we do all of our decisions in the world and based on a consensus protocol? And you know, the answer is maybe not everything. We're going to tell you when to make those decisions, but the most basic form was the idea of a smart contract. So let's talk about what a contract is first in the traditional sense. A contract is some sort of agreement that you come to with another party. 2 parties coming to agreement and putting it into a contract. And the idea is that you write this contract with some sort of like muscle behind it, right? You have a law enforcement or a justice system that ensures that nobody's going to violate this agreement. And that's the goal of writing a contract. But of course, like the English language and other human languages have ambiguities and are open to interpretation, and contracts are violated all the time. And so some people had the idea of a smart contract. So Nick Szabo coined this term smart contract in 1996, and he said, why don't we take the terms of this agreement and we can write it into programmatic code, which is deterministic, right? If you run a contract, or if you run a code, no matter how many times you run it, it's always going to give you the same output. we won't get into the details of that. But the idea is, why don't we take all these agreements that we make and then have some piece of code do the actions for us so that we don't need to trust somebody to do what we want them to do. Obviously, the caveat to this is you need a trusted entity to run this contract and make sure that it gives the output that is like true. Okay, so in comes Ethereum. Ethereum, this is their homepage, markets themselves as a blockchain smart contract platform, which means they enable smart contracts and they take away this trusted entity and replace it with this trustless distributed network that we got from Bitcoin. So this is a high-level overview. They basically let you have smart contracts on this distributed network. You can think of the Ethereum network as like a distributed computer that executes smart contracts and has like a network state. It's like its own little world, the Ethereum world, and then you have smart contracts and transactions that happen between people and contracts that can change the data or what's going on in this world. So this is not too different from Bitcoin, actually. So Bitcoin's world is a transaction system, right? It's a list of who owns which Bitcoins. And so every time you send a transaction, you are transferring ownership of a Bitcoin from one person to another. So that's the change that you're making. But in Ethereum, since you have smart contracts and you have more complex things that you can do with smart contracts, these changes can be different. It can be more fancy than just transferring ownership. And so fundamentally, Ethereum is a cryptocurrency. So their native asset is called Ether. How many of you guys own Ether? A couple? Okay, chill. Yeah. Yay. Okay. But the thing about Ether is, even though it is the cryptocurrency and it's the basis of value in the Ethereum network, it's not really the most important thing that Ethereum is centered around. Like, always remember that Ethereum is a smart contract platform. So a lot of times Ethereum is hailed as like Bitcoin 2.0, and I really want to emphasize the differences between the two, even though they have a lot of similarities that I discussed, that distributed network. They both have those three core components that I talked about. And so one question is like, as people saw like distributed ledger technology, and they were like, oh, let's build like decentralized, autonomous organizations. Let's start a whole new country where everything is governed by smart contracts. But, a lot of people had these ideas, but it was like, should we build it right on top of Bitcoin? Because that would make the most sense, right? It's an already established network. Its security is like well tested. But the obstacles that they ran into were like, Bitcoin is very simple in its scripting language. It doesn't have very many functionalities, so it's hard to do these. It's hard to implement these fancy like things that you can do with smart contracts. And also, the Bitcoin community is quite conservative when it comes to adding new things to their protocols. And so Vitalik Buterin here, he decided it's time to move on to like bigger and better and like Turing complete things with a different platform. And so let's spend some time comparing the two, Bitcoin and Ethereum. So like I said, Bitcoin is very simple, and that's because it was designed to be like the most plain version. It's just a transaction system, so it's like robust and secure. Like, that's what it's supposed to do, and because of that, it's often regarded as like the gold standard of cryptocurrencies and blockchains. So the idea is like, if Bitcoin, which is like the most basic flavor, fails, then all cryptocurrencies could fail. And on the other hand, Ethereum has this like new flavor of like smart contracts. It's more complex. It has more features. Its scripting language is Turing complete. And so you can do a lot more things with it. And even though it has this asset, Ether, it's a very like secondary purpose in Ethereum. It's mostly used to align incentives. So for example, miners are rewarded with Ether when they add new blocks to the network and help secure it, as well as the people who execute the smart contracts are also given a little bit of Ether in order to pay for this computation that they're doing. They both use proof of work at this moment, but I think Ethereum is planning to move on to proof of stake within the next year or so. Okay, and some implementation details of Ethereum. They have a different block time of 12 seconds, which is significantly shorter than Bitcoin, which is 10 minutes. And why do we want this? Because we're doing smart contracts, which need to be executed and changing the state of the network like quite frequently. Obviously, the block reward is also different in that case. The exchange rate, I have learned my lesson, and I'm going to put up charts from now on because anything I put on a slide is always inaccurate within the next like minute or two. For example, when I saw this slide that I was supposed to edit, it said 17. $17. And I was like, wow, that is so different. And it was from last semester too. So this is like this year's Bitcoin or Ethereum prices. And you see the lowest is like not even, is zero. The lowest is zero. Like it was that close to zero, and the highest is 400. So pretty cool. But we don't like talking about price. So I want to talk about the fact that Ethereum uses accounts as opposed to UTXOs. So UTXOs were kind of difficult when we were trying to understand them in the context of Bitcoin, but I do want to remind you guys that, it makes a lot more sense in Bitcoin. They were trying to solve the problem of double spending, and they wanted to make private transactions from different people. And so it's very easy to just say like, oh, here's a UTXO. It's a spendable piggy bank that we pass around between people. Or we don't pass around. We create and then we destroy. And that's how Bitcoin gets transferred between people. And once it's spent, it can't be spent again. Very intuitive way of solving the double spending problem. And from a validator's perspective, all you need to do is keep a list of these piggy banks. And then as soon as someone spends Bitcoin, you can just get rid of it and then replace it with a new one. That's all you need to take care of, which makes sense in the Bitcoin network. But on Ethereum, we have more complex things going on. We need to write smart contracts where we can really easily send Ether from one account to another. And so it doesn't really make sense to like aggregate all these UTXOs and then figure out a way to do it that way. And plus we need a lot of other data that needs to be stored as well. So because of all these like fancy things, Ethereum uses accounts. So I just wanted to talk about the rationale behind that. So a little bit more about Ethereum accounts. There's two types. Make sure you know the difference. People have lost a lot of money because they didn't figure out the difference between the two. So if you and I make an account on Ethereum, we have what's called an externally owned account. So this is usually owned by users or organizations or corporations, whatever. And it's basically a basic account. You have an address that people send you Ether with, and then you have an Ether balance, obviously, like that's how much money you have, as opposed to like owning a bunch of UTXOs. And then if you write a smart contract, that contract will have its own account. And this is very important. Like contracts, you can consider them as like independent entities on the Ethereum network. So they own their own account with their own Ether balance, with their own like code and storage and everything. And then so smart contracts are like autonomous agents on the Ethereum network. So you can tell a smart contract, okay, I'm going to send you this amount of money, and then you're going to do XYZ with it based on like the functions that you have. Or let's say I want to call one of the functions in an Ethereum smart contract. I can do that, and it will output something that either changes the network state or changes the balance of Ether in different accounts. And the way it does that, or it can do that using its like control over its own Ether balance, its own contract state, as well as being able to like write to the blockchain and make changes to the network state. Okay. And generally, Ethereum contracts will serve 4 different purposes. They're very this is just a way of you guys classifying like the information. So the first is to store and maintain data. Some data that you want to put onto the blockchain, you can do so through a smart contract. Obviously, you don't want to store everything on a blockchain. I really want to stress that is very important. And Aparna is going to talk about like what you would want on a blockchain. Another is to manage contracts or relationships between untrusting parties. So this is the most basic sense of a smart contract, right? You can trust that this smart contract will do something for you in mediation between you and this other person that you're contracting with. And then they can also provide functions for other contracts. This is a very like basic coding kind of thing. So for example, there are like mathematical function contracts out there that you can call, and you can say like, oh, I want you to add this for me, or like some more complicated math function, and they're considered like very secure in how they calculate it for you. And so that's how one contract can be used. And then the fourth is complex authentication. So for example, multi-sig, that's also possible in Bitcoin, but we have contracts that do interesting like financial transactions in Ethereum as well. And of course, a contract can do any four of these things in combination. So yay. Here's an example of a smart contract. Don't like worry about being able to read it, but this is written in Solidity, which is the most common Ethereum scripting language for writing smart contracts. This is actually the homework for our other decal, our developers decal. So if you're interested in this kind of stuff, you are taking the prerequisite for this class, so you can take it next semester. But basically, this is a betting contract. And so let's say Aparna and I want to enter into a bet, and we're like, let's say this was like 2 years ago, and we're like, who's gonna win the presidential election? Like, let's say I was like, oh, I think Hillary's gonna win, and then she was like, oh, I think Trump is gonna win because she loves Trump or something. And then, so we can basically use a smart contract to make a bet, because like, let's say like we are salty people, and like if we lost, then like we wouldn't pay out. So like, let's say we didn't trust each other. Obviously, we're friends, so we wouldn't do that. But let's say we needed to use a smart contract. So at the top, like one of us would be Gambler A and the other one would be Gambler B. And then the contract would keep track of our addresses so that they can send money to and from, they can send money to us. And then so you have a bet, that's a struct that you can define. And then you have who bet on what. So it'll be like I bet on Hillary and Aparna bet on Trump. And then the winnings, which is keeping track of like who won how much money after the bet returned. And so you have these three different functions. Well, you'd have more functions, but I just shortened it down to three. I mean, these are basically like the powers that you grant your smart contract to be able to do, and the exact powers that you let them do. Like that's the nature of coding, is you specify exactly what it can do. And so for example, make bet. So Aparna and I will call this function and say, I want to bet on Hillary, I want to bet on Trump. And then make decision, we'll have some kind of trusted oracle decide like, oh, Trump won. And then so the smart contract would take that data and be like, oh, that means Aparna's winnings equal the total ether balance, and then Gloria gets 0, right? And then withdraw is a function that Aparna can call and trust that the smart contract will give her the right winnings that she has earned through this bet. So this kind of makes sense. Oh. So smart contracts, we know what that means. We kind of know what Ethereum is. Yeah. Okay, so an oracle is basically some kind of source of information in like a smart contract. We call it an oracle because it's like trusted and whatnot. So the oracle will be another address in this case, or another user. And so you can specify like who is your trusted oracle, and then later when the decision is made, basically the oracle will use that function to input the data of like who won, and that will influence how the contract makes decisions. Does that make sense? Okay, cool. Awesome. Okay, so the Ethereum virtual machine is like how these contracts actually get executed across the distributed network. So it's actually not the contract code that I just showed you that is directly executed. It's actually compiled into EVM code. This is very similar to assembly language, if any of you have taken 61C. It's basically, we take all this complex, like all these cool features, these loops that we like wrote into this language in Solidity, and then we compile it down into something much more simple, something stack-based, where you just give the machine a list of instructions to execute. So let's say you had a loop, then you would like break it down into like doing this over and over again. So this allows us to have all these complex Turing complete, blah, 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 whatever, in our smart contracts, and then still trust that the machine has like a deterministic, like standard output afterward. And everyone on the Ethereum network, if you are a validating node, everyone downloads this standard software, and they all use the Ethereum virtual machine within their computers to execute these not the smart contract, but the EVM code. And so the idea is like, let's say my computer is different from yours, like I have a different processor, or like yours is faster, mine is slower, whatever. This like gets rid of all of the differences in how we could possibly execute this code. So everyone gets the exact same results, and that's how we come to consensus. Yeah, this is just what I just said. I'll explain on a slide. So yeah, EVM code is the low-level stack-based language. You have your high level, and it compiles down into a low level so that the machine can like do what we want it to do. And the really cool part is the compiler that lets us funnel all of this amazing, magical things that we wrote into the smart contract into something that is deterministic and simplistic and gives us the right answer, basically. And so obviously one issue that comes up is basically if I'm an attacker, I can look at the Ethereum network and it's basically a bunch of computers and I can force them, well not force them, to run a code for me. So that's kind of a lot of power that you have if you are writing a smart contract. So let's say I wrote a smart contract that was just an infinite loop. In this box right here, like, oh, just keep on going forever and ever. That would really suck for the network because everyone would just be wasting their computational power trying to get out of this loop, and they never would, right? This contract would never terminate. And so this can lead to a denial of service attack. Like, let's say I want Ethereum's network to go down. All I have to do is send in this contract, and then suddenly everyone's computers are like stuck in an infinite loop. That's not very good, right? And if you've taken CS70, you know that by the halting problem, it's impossible to tell whether or not a piece of code will terminate unless you actually run it, right? And so this is a problem, and we need to solve it somehow. An Ethereum solution is really cool. They use what's called gas, and gas is paid for using Ether. And the idea is every time you call a function from a contract or you poke a contract to do something for you, you also need to feed it some gas in order to fuel this Ethereum virtual machine to execute the code for you. And so you'll specify your start gas, which is the maximum amount of gas that you are willing to spend on the smart contract. And then you'll also specify the gas price, which is like the conversion from Ether or Whey to gas. Like this is one of the quiz questions. Did you guys get this right? Nice. Okay, so yeah, Ether prices change all the time, so we use this gas price in order to make sure we're paying a good. Yes.
Wait, question? Does the user specify the gas price?
Yes.
Can you just
or
make your gas price 0 or really small?
Well, then nobody would execute your code.
Oh.
Yeah. So that's a very good question. So his question was, why don't you just specify a really cheap gas price? And so as a validating node on the Ethereum network, you get to choose which contracts you're going to execute. And so people who aren't going to pay you enough money, you don't need to serve them if you don't want to. And people who pretend like they use like a very high maximum start gas, you can just call BS on that. And you know you're not going to get paid that much. And the reason is on this next slide. So basically what happens after you put in this gas is if the smart contract executes all the way through and you didn't use all of the gas, it's refunded back to the person who gave all of this Ether. And if it doesn't execute, or if it goes into that infinite loop, at some point it's going to run out of gas. The contract will revert all the changes that it tried to make and not refund the money. So anyone who tries to launch an attack like I just described, the denial of the service attack, will not get their money back if their smart contract doesn't go through. And so you can think of gas as the price that you have to pay in order to use this awesome, trustless, decentralized computer and to run these smart contracts. Okay, and if you're an attacker, you need to have a lot of money in order to force everyone to run an infinite loop. Okay, so one last reminder is basically Ethereum has this like network state, this global state that it holds using this state that it holds with like all of the addresses or all of the accounts and their balances, how much Ether everybody owns, what the data is, and all of the smart contracts, and it keeps track of this. And every block that you add to the network basically changes the data. It updates this network state. And so you can think of the Ethereum virtual machine as like a state transition function. It'll take the current block state, it'll take some gas, and then it'll take some memory that it uses, and then transaction, a message, the code, as well as a stack and a program counter. Those are like, you don't really need to know about those details, but basically it takes all this information and it outputs a new block state and whatever remaining gas that it has after execution. This is just a graphic from the Ethereum white paper. And in the extra slides, if you look at the slides later, there's another block diagram with like what a block looks like in Ethereum as opposed to Bitcoin. So you can kind of see the differences and like the complexities that are introduced with Ethereum. And then, so a few conclusions. So the Ethereum network and all the designs that it has is designed not to be efficient in computation. It's designed to have a trustless execution and consensus on what the execution result is. And so because of that, it's very expensive, first of all, and it also creates an incentive to not use a blockchain when you're thinking about the decisions that you want to make. And so Aparna is now going to talk to you about like how to make these decisions when you're talking about, whether or not you want to put it on a blockchain. Cool.
Okay, how's everyone doing? Still awake? Okay, so let's talk about some use cases, and let's get started with basic use cases of smart contracts. So one way that Ethereum likes to market itself is by saying it can implement all the complexities of Bitcoin in just 4 lines of smart contract code. And this is an example of that from the Ethereum white paper. All you have to do is check that if Alice is going to make a transaction to Bob, she has enough money in her account, and that she initiated the transaction. And then you subtract that amount from Alice and give it to Bob. Pretty simple. Another interesting application of blockchains could be having a decentralized server system. So how many of you recall back in 2016, around October, a denial of service attack when Twitter, Netflix, and all these websites were down? Do you remember that? So instead of having a central server, if you have a decentralized system, you could just have a system where you map domain names to IP addresses. So Mac's personal website, maxfang.ng, could map to 696969. And the advantage of using a blockchain is just because a central point fails doesn't mean your website is going to be down. So another very basic use case is called proof of existence. This is actually something I worked on over summer, like a couple-day hack. And it's a simple way of proving that someone owns a document without revealing the actual document. So you take a hash of a document and put it on a public blockchain like Ethereum or Bitcoin, which has timestamps. And later you can prove to anyone that you own the document as long as you can hash it. So for example, if I was going to use my computer and rent out storage space to Gloria, and she wants to store a document on my computer, I'll do a proof of existence on the blockchain. And later, if she wants to know that I'm still storing her document, she asks me for the hash. If I give her the hash that's on the blockchain, she knows that I'm still storing her document. Moving on, let's talk a little bit more about,
Question.
Yeah.
If in that example that you just gave, if as soon as you went out the laptop, you did the hash,
Yeah.
and then you stored that hash somewhere in the notebook,
Yeah.
and then deleted it, and then she asked for it a year later.
I could just give her the hash. Yeah, that's right. So if you want to be more tricky, Gloria could just tell me to hash the document with a random number of her choosing. So then if I can produce that, and she has all these hashes stored, she knows that I'm storing it. Yeah. Good question. So how many of you have maybe personally, directly or indirectly experienced land-related disputes? Okay. So my neighbor had to inherit a piece of land, but because of bad paperwork and really shitty documentation, he had to go to court and fight it out for 10 years. And this is in a country like India. So think about how it could be if tomorrow you had a hurricane in California and you were forced to evacuate. All the documents, all the papers are wet and lost. How do you prove that you still have ownership of the land underneath your house? So one potential solution is if you have a trusted central government that's in charge of keeping all these records. But of course, the drawback to that is you could have corrupt officials who your neighbor could bribe just so they can get a piece of your land. Also, not all governments may have enough resources to support such a central infrastructure. So enter the blockchain solution. The blockchain solution basically takes a hash or a digital signature of the document and puts it on the public blockchain. The actual document can be stored in a central database just so you don't have to replicate all that information. Because remember, storing on the blockchain is expensive. The benefit of using the blockchain is tomorrow if you came back after the natural disaster, it's immutable, so your records have not been lost. And in case someone claims ownership of your land, you have this transparent database which you can both access to know that it's clearly you who owns the land. And the actual best part of using a blockchain is transfer of ownership is very easy. It's almost as easy as making a Bitcoin transaction from your Coinbase account. You don't need government officials, you don't need third parties. It's just one click. And you could have a smart contract kind of escrow account so that if Gloria wants to get my land, as soon as she fills up enough money in the smart contract, the funds get released to me and the land gets released to her. So some countries like Georgia, Ukraine, and Sweden are adopting this. The caveat with this blockchain use case, though, is that you still need to trust that the endpoints that are entering information are being honest, and it's a little tricky to associate physical land with virtual identities that you create for the land. I mean, which is why you could have like satellite imagery or satellite measurements, but yeah. Okay, so let's talk about another interesting use case. How many of you have heard of prediction markets? Okay, so prediction markets are a great way to draw on the wisdom of the crowd and predict what could happen in the future. And the market makers basically have just one job: create an event that is public, easily verifiable, and has a set due date. So for example, one of you could create a market on who would win the 2020 US presidential election. If you believe in Trump, you could buy Trump's shares. If someone else believes in Zuckerberg, they could buy his shares. On the election day, once the election's over, you have these entities called oracles who feed in information about the actual result onto the blockchain. And then based on what these majority of oracles voted, the money gets paid out to the right parties. Prediction markets are great ways to figure out the probability of an event actually happening. So, for example, if some event is never going to happen, its shares are going to resolve to $0. And if someone had, say, insider information about Hillary that they were going to leak at this election, they could buy a bunch of Trump shares, stock up, so the price goes to maybe 70 cents for Trump's shares and then 30 for Hillary, and then release that information, making a bunch of money. Yeah. So other use cases could be, you don't just have to create markets for elections. You could also create markets for, say, is this movie going to be a flop? But what does flop mean? So maybe is this movie going to raise less than $100 million? And this kind of incentivizes those with insider information to bet and let the other people know what the probability of an event actually happening is. Another very interesting use case is hedging and insurance. So you could bet that your house is going to burn down by a certain date. And then an insurance company could bet against it, claiming that your house won't burn down. And if your house does burn down, you get the money. If it doesn't, the insurance company takes your money. So, yeah. And because you don't have this like middleman, you get to make all the profits. Other commonly used use cases are as security bug bounties. So Augur and Gnosis are both prediction markets on the blockchain, and they both secure their code through creating bug bounties on this platform. So what that means is you could set a date and put a market out to the public that my product is going to be hacked, and the hacker is going to reveal his exploit to me. If that happens, you pay the hacker and you learn to secure your code. Hopefully the hacker reveals his exploit to you. Another great use case is if you're if you're going to run a Kickstarter campaign, or if you have a company that you're going to launch, to give your investors more confidence that you're going to meet your deliverables, you can bet some money and say, I'm going to launch on the date that I promised. If you don't, then you pay out your investors. If not, your investors pay you. So prediction markets don't necessarily have to be decentralized, but there are a lot of benefits. Like number one, you have no restrictions on what markets can be created and who creates those markets. But that also means you can create illegal markets like assassination markets. So maybe I could create a market on, hey, is Gloria going to die by the end of this week? And she might vote yes, and she might be paying for her own assassination. Because if she votes yes and then someone else votes no, they're incentivized to kill her and take the money that she put in for yes. Anyway, so Augur tries to get around this by having the oracles vote on whether a market is ethical or unethical, but you're kind of trusting these oracles to vote honestly. That's kind of an iffy line. If you assume majority of the world is honest, I guess it could work. Another advantage of being decentralized is instead of having each country have its own little betting market on sports or something, why not expand that out to the entire world? That way you have a shared liquidity pool. And of course, it's censorship resistant and automatic. Questions on that? Yeah.
Could you further elaborate on the role of the oracle and who performs it?
Okay, so oracles are basically like shareholders in Augur who do this job of feeding in external data onto the blockchain. Because right now there's no way to bring in data from outside. It's only what is already in the smart contract. So oracles are people who you assume are going to vote honestly, because if they don't, they lose a share of their money for voting dishonestly. But again, honest depends on what the majority voted. And if majority voted a certain way and you were still honest and voted in the minority, you're going to be punished.
So the lead-on question is, what's the scalability
Of oracles? Well, again, yeah, you're kind of relying that they are going to be active. If they're not active, then the system fails again. So a lot of assumptions that you're making. Yeah. Land titles is one of the best use cases for blockchain out there right now. The other ones that we see are good use cases, but not the best, as we'll see. So let's talk about supply chain. How many of you have heard of blood diamonds? Okay, so for the rest of you who don't know, it's basically in these war-torn regions, you have gangs fighting each other, and as an honest citizen, you might want to know if someone died in the process of mining your diamond. The Kimberley process is a governmental effort that requires all the participants to certify the origin of their diamond. However, if you're trusting government officials to give out these certifications, you could just bribe them to sign whatever. And this, of course, masks the actual trail of the diamond. So you could own a bloody diamond but think it's not. So Everledger uses a blockchain to track the path of these diamonds. So every diamond that exists will have a corresponding digital identity that's created and put on the blockchain. As this diamond moves along the blockchain, you also transfer the identity of it, or the digital counterpart. And if, say, you are someone who's just receiving the diamond without the digital identity, you wouldn't want to accept just that because you can't prove to someone later on that your diamond is not a blood diamond. Of course, advantage of using a blockchain is that the history is immutable and no one can tamper with any of the records in between. If you're an individual who's receiving the diamond, you'd also have to match up the actual diamond with its digital identity and see if they correspond. So that's why Everledger is a decent use case, but this is not true for all blockchain use cases for supply chain. The main drawback being there's no clear-cut way on how you can match physical goods with their digital identities. So for example, if I were to take that dustbin, and if that had a unique ID, if I were to break that, I could just buy a new dustbin, graft the same ID on it, and pass it on to Gloria, and there's no way she can know that it's been tampered with, or it's not the real good that I say it is. Diamonds are a good use case. Other luxury goods or pharmaceutical drugs, anything that you can create unique identifiers for, you can have the supply chain on the blockchain. But again, the caveat is that you're assuming that the entry points of information are honest. Questions? Okay. So let's now talk quickly about DAOs. DAOs are decentralized autonomous organizations, are these bodies that can be completely governed by code and math. They rely on this principle of code is law, as Gloria talked about earlier. Some issues with DAO are that code once put on the blockchain is immutable, so it's hard to edit the governing code, the governing laws, once you make them. And another issue is you could have inactive participants or inactive people who hold these tokens and just don't vote. And there's nothing you can do about that. So let's now talk a little bit about generalizations, as in does it make sense to use a blockchain? So these are 5 questions you should be asking yourself in order. And if the answer to every single one of these is yes, then you're okay using a blockchain. The first is there a shared database? Is there a database at all? If not, don't be using a blockchain. Are there multiple people writing into your shared database? Are there multiple points of information entry, information modification? That's your second question. The third is, do these multiple entities kind of mistrust each other? If they completely trust each other, there's no reason for a blockchain to exist because they could just rely on a central database and everything would be okay. The fourth question is having a trusted intermediary a risk of any sort? If not, it's way more efficient to just go that way. And the fifth is there any kind of interaction between transactions? So what I mean by that is there should be some kind of transaction dependency by the different writers to the database. So an example in Bitcoin would be if Alice pays Bob 5 Bitcoin and Bob pays Charlie 4 Bitcoin, the fact that Alice paid him 5 Bitcoin gives him something to use to pay Charlie. And his transaction to Charlie kind of depends on Alice's transaction to him. So, let's see. Oh, yeah. If you don't have a shared database, if you don't need a shared database, use some other regular file storage system. If there aren't multiple writers, just use a central database. If there's no absence of trust, you can just create multiple copies of the same central database and everything should be fine. If having an intermediary is not a risk, use a trusted third party. And finally, if there is no interaction between your transactions, use a master-slave database replication system. So those are, again, ways for distributed consensus, just without all the complexity of blockchains. And they come under a category called classical consensus algorithms. Okay, so here are some limitations of blockchain technology. One is there's no trusted way to bring in external data onto the blockchain. So you're kind of forced to trust oracles, as we saw in the example of prediction markets. One possible solution is using an untrusted oracle or something like oraclize.it, but that has a very shitty implementation. Yeah. Other solutions you could rely on would be having an oracle network, which is kind of like what he mentioned. How do you know that the information that the oracles put in is actually honest? So you could have some kind of consensus mechanism amongst themselves, but that adds in too much of complexity. Think of a consensus layer on top of a consensus layer. The third solution is to use trusted executable environments like SGXs or ARMs. So as long as you can code in C and you're happy doing that, you can use those. Again, you're trusting Intel or whoever manufactures these hardwares to do a good job. Other limitations are there's no way to enforce on-chain payment and contracts cannot manipulate confidential data. So you cannot implement things like loans and bonds because there's no risk of default. So this slide captures all the interesting properties that we saw in all the blockchain applications today. So trustless environments that come to consensus and coordination we saw in the example of land titles. Augur showed us how blockchains help create censorship resistance or disintermediation, and Augur is like a new way to create incentives for people. We also looked at new governance models like DAOs and Futarchy, if anyone's familiar with that. And we looked at the concept of programmable money in the context of Bitcoin or Ethereum. Not to say that US dollars cannot be programmed, it's just that having a blockchain underneath allows for other properties like micropayments. And one takeaway is always ask, why is using a blockchain better than a central database? Some trade-offs you have if you use a blockchain is you lose on efficiency and you lose on any kind of control over the system. Like, if those are properties you're looking for, do not use a blockchain. Conclusion. So blockchain is a great technology that can be disrupting, but it is also very crucial to always ask, why is blockchain better than using a centralized database? I've had lots of people come to me and talk about use cases just to append the word blockchain because it sounds cool. But don't do that. You lose efficiency and other important things as well. Okay. Oh, if we actually have a couple minutes, so I have an example of a bad use case if anyone wants to brainstorm. So you have an airline industry where you have different flight companies that don't have access to each other's details. So what could you do to get around faster when you have a flight cancellation? How many of you have been stranded at an airport just because your flight got canceled? Few days, few hours, very messy, right? What if Delta and American Airlines shared all the information of flight status? Is it overbooked? The times that it's departing? Can someone book themselves onto another airlines? Wouldn't it be so much easier? So, what do you guys think could be a possible solution here? Does this make a strong enough case to use a blockchain? Yes, no? This is supposed to, oh yeah.
Like I think that like in this case like there are like pros and cons for both sides. So like one was that like the need for a shared database, like you said, was one of the prerequisites.
Mm-hmm.
But there's also the problem that they're looking for a fast and efficient way.
Yeah.
Which blockchain isn't like the perfect solution for.
Yeah. So what could they use if you remember those 5 questions and 5 different solutions?
Well, like the one on the screen, I guess like a common shared database.
Okay, so what are common things that they have? Like, which 5 of these questions? Number 3? Okay, yeah, exactly. So they could just use multiple copies of the central database. Yeah. Cool. That's pretty much it for today's lecture. Yeah. Those were extra slides. Okay.